I'm going to tell you about flavor physics at LHCb. So Sergei explained you what is the B. So when I write flavor physics, in fact I mean B physics in that case. So Sergei explained you the theoretical basis you need to know, and I will build on that. So this is the outline of what I'm going to discuss. So in order to get a little bit of rest after the theory given by Sergei, I will describe what is the LHCb detector and what is useful for doing the physics we are doing. Then the two last parts are really physics analysis and physics results. Some very last one we obtained in LHCb. I know that you are students and you are not attending a conference. So, but at the same time, I wanted to give you some very new results. So I have chosen to just discuss some example of results and trying to explain you what is really in the analysis, how the analysis is done, and how to understand the results from a physics point of view. So of course I will not describe all the results by LHCb. Otherwise it will take much more than the 3 hours. So I'm going to speak for 1 hour and a half, and tomorrow it will be the second part, 1 hour and a half. I don't know where I'm going to stop in that, we'll see. So, the LHCb detector. So this is a sketch of LHCb, and this is somebody at more or less the proper scale, so to give you an idea of the size of this detector. So the LHCb detector is, as its name indicates, located on the LHC accelerator. And for the very young student, I just remind you that LHC is an accelerator, look at that CERN, colliding proton against proton. It's a 27-kilometer ring, about 100 meters underground. And the protons are colliding in 4 experimental points, where there are, of course, 4 detectors, and that's 4 experiments. The 4 experiments, so there are the 2 big ones, which are ATLAS and CMS, and these are the ones which discovered the Higgs boson in July 2 years ago, 1 year and a half ago. They are also searching for physics beyond the standard model and measuring precisely properties of top quarks, for example, or electronic physics. There is the ALICE detector, which is meant to study heavy ion physics, so to study quark-gluon plasma. And the LHCb detector, which I'm working on, as is Sergei. And so I'm going to give some results of this detector. Okay, these are the 4 experiments. So, because it's working at the LHC, in fact, the LHCb detector has this very peculiar shape you've seen on this slide. So you see it's a forward spectrometer. Why? It's because the B and B bar quarks are produced through the collision of a proton and another proton, and in fact from what's inside the proton, so the quark and the gluon. And because of the energy sharing inside the proton, the 2 B quarks, or the B and the B bar quark, the BB bar pair, is going to be produced very much forward or backward. You see here the angles, and you see either it's going B and B bar very close in this direction, or B and B bar very close in this direction. So in principle, you would build 2 detectors, 2 forward spectrometers, one like that, the other one like that. And you have the BB bar either here, or the BB bar here. But no BB bar here and there. Okay. Because of the size of the cavern to dig, because of money constraint, and so on and so forth, only this exists. and two B quarks are produced, and as Sergei said, the B quarks do not, as any other quarks, they do not stay naked, and they just hadronize and form B hadron. And for example, here it can be a BS and another B hadron, which then further decay into several particles, which some of them we want to use and to identify the type of the B hadron which is produced and to study its properties and the special properties of a given decay. So all that drives the design of the detector, because the B hadron lives for a long time, about 1.5 picosecond. Then, because of the high energy at the LHC, they have a significant boost, and they will fly for a significant time, about a few millimeters. So forward and a flight. This is a distinctive signature of a B hadron. It flies from the primary vertex, so the collision point, we call it primary vertex. It flies for a significant distance, and we want to identify, to use this as an identification tool. Also, you see that you have muons, kaons in the decay, and all these we want to be able to recognize and to distinguish pion from kaon from muon. So this drives the detector design. But I told you that we have the hadron producers, those in red or in blue here. But you see these black tracks. They are also produced, and they are linked to the hadronization process and to the remanence of the protons. It means that we have many other tracks in the detector, and this is complicated and not a very clean environment from an experimental point of view. In one collision, we have about several tens of tracks. It's a lot. It's busy events. We also produce all types of B hadron. When we have a B quark, it can hadronize into a B plus, if it hadronizes with a U bar, or a B0 D, if it hadronizes with a D bar, or a B0S with an S bar, or it can give B hadron if it pops a diquark from the vacuum. So the fraction of cases where it hadronizes to a B or a BS has to be known and measured. So, but not only B quarks, BB bar pairs are produced. Many other type of events. So just to give you an idea, so this is at 14 dB the total cross-section, which is about 100 millibar. And you see that the BB bar cross-section is about 500 microbar. So really the inelastic one is where we really produce some tracks. So you have to compare with that. But you see it's about a factor 160. It means that the background is 160 times larger than the signal. So we will have to do something to recognize the signal. We are not going to write on tape 159 uninteresting events. Okay? So we need to find a way to recognize those interesting events. And we're going to use what I just said before, trying to recognize the muon, trying to recognize the kaon, using the fact that there is a flight. But even this, which I told you is so small compared to the background, yet in every 200 collisions, there is a BB bar event. It's huge. There is 40 megahertz of collision at the LHC. 40 megahertz. And in 1 over this 200 of these, there is a BB bar. It's a huge number of BB bar events. And so we have to do something because we cannot register all of them. And most of them, we don't really care. So this is what we call trigger. So we need a trigger to reject the light quarks, the U, the D, and S, and to keep only the interesting B events. a very precise silicon detector, we'll come back to that later on, which helps to identify the fly of the bee hadron. Okay? Then there are some rich detectors, so for the Cherenkov, rich 1 and rich 2, and they help to identify the kaon, which is another way to tell you I have a bee hadron. Then you see this big thing, this is a magnet, because here we have no magnetic field. The tracks go straight. They go through the velo, they go through the reach, they go to the tracking station here, and then they are bent in the magnetic field, and then there are some other tracking device there. So because they are bent, we can measure their momentum and their charge. Then we search if they are pion or kaon, and then they enter in the calorimeter. The calorimeter will give you the energy on the information on the energy for the electromagnetic particles, light blue, and the hadronic one. Later on, this is the muon chamber, so all the other particles are stops, but the neutrinos, but you don't see them, but the muons, so if we have heat there, we know this is a muon track. So with all that tool, all those tools, you can know if you have something which fly as a bee, if you have kaon, you have a lot of kaon in bee decays. If you have muon, a lot of muon in bee decays, and you can see electrons because you have a lot of electrons in bee decays. This is, I told you the events are, there are a lot of tracks, and this gives you an idea of how many tracks on a random event. This is a real event we have. So in the middle of all that, we have to find the proper tracks which are really coming from the bee. So the crucial point is the tracking. And I just want to spend some time, not a long time, to describe you what is the velo detector. So the velo detector spreads around 1 meter. There is 21 discs of silicon. One is here. So the beam here is that in the horizontal like that. And in there, it's coming from your side and from behind the screen, okay? So this velo detector, it's a disc of silicon, and in fact it's 2 half discs, like that, which can open and close. Why is it so? Because maybe you've learned on a silicon detector. These are very fragile detectors. And the LHC beam is a terrible beam. There is a huge amount of energy stored in the LHC, so, and potentially a lot of radiation damage if the beam goes through nearby the detector. So what happens is that this half disc, it's open when the LHC is adjusting the beams and so on and so forth. And when they declare stable beams, at each run, we just close the velo nearby the beam. At the end, it's very close by the beam. It's about, you see, it's 8 millimeters from the beam, the active zone. This type of detector allows very precise impact parameter resolution. The impact parameter tells you for a track whether it points or not to the primary vertex, for example. Okay? So, and the resolution is about 20 to 30 microns. It means that if there, so this is the primary vertex where the 2 protons collide. Then you have a bee which flies and then decays. Let's say it decays into a K- and a pi+. But I have a lot of other tracks in the events coming, a lot of them coming from the primary vertex. And what I do for each track, I compute the impact parameter. The impact parameter is I extrapolate the track and I see whether, what's the, well, I see in fact like that, the distance through the up to the primary vertex, okay? If the track is coming from a bee decay, it has a large impact parameter. If it's coming from the primary vertex, it has a 0 impact parameter. So this is a very powerful way to identify the track coming from BDKs. And this detector helps me with its very good resolution of the order of 20 to 30 microns. But you have to keep in mind that at each run it gets open and closed. So if some of you are doing experimental work, you know that when you're moving a detector like that, you have to realign it afterwards. Okay? And it can be realigned to 5 microns. I can explain later on. So this is some plots to give you an idea of how well the tracking is working, and also how well we can reconstruct some particles. So for the younger students, so to reconstruct the invariant mass of a particle, we are using energy momentum conservation. We are measuring the energy and the momentum, and then we can compute the invariant mass. And we can do some plots like that, and you see that we have some peaks, for example, at the lambda B position, at the BS, or even B sub C, which is a weird B meson formed by a B quark and a C bar quark. And you see the mass measurement, which have uncertainties of the order of few 10 to the minus 5, so extremely precise. Because of careful calibration of the velo, the vertex locator I've shown you, but also the tracking as well as the magnet. So I told you that we need to identify kaon, and we identify kaons through Cherenkov effect. So the Cherenkov, so you probably all know how the Cherenkov effect works. The idea is that when a particle goes through a medium, it emits Cherenkov light, which angle is related to its velocity. If the beta is greater than c divided by the index of the medium. So doing that, measuring this, since p is known from the tracking, then we are able to measure m. And so say whether it's a kaon, which has a mass of 500 MeV roughly, or a pion, which has a mass of 140 MeV. So this is how we recognize kaon from pion. And this helps us because in background tracks we have a lot of pions and no kaons, nearly no kaons, while in tracks from BDKs we have kaons. And this gives you an idea of the performances, and for about 85% probability to identify correctly a kaon, we call a pion a kaon, so we do the mistake for about 5% of the cases. Okay, so just to tell you that I told you that we're also measuring photon, electrons, and hadrons, and I show you this decay, the BS25 gamma, and so we recognize the gamma in the electromagnetic calorimeter, and there is a resolution which is of the order of 100 MeV. So it's not as good as for the track, because when you start to measure neutral particles, you probably learn you're losing a lot of resolution, but still there is a clear peak, and we can use it. I'll show you in the very end. So last point is muon chamber, and we identify about a very high fraction of the muon, about 97%, and we are mistaken for the pion for a few percent. So it's basically, it's not very complicated to identify muon because they are the only particles which are passing through all the other detectors. So at the end, it's shielded from all the other detectors, by all the other detectors. So what I've said before is the example of LHCb, but most of the particle physics detectors are working that way. What is different is that LHCb is working at the LHC. And LHC is a machine with a very large luminosity. a very large luminosity gives you a large number of B events and a large number of X events and everything, but it means that each time the proton beams are crossing, you can have several collisions. This is what we call pilot. So you don't see it very well, but here, these are the velo station I've described. Remember the disc, silicon disc, you see them here. So it's a zoom of an event display. And the four white circles are where we reconstruct primary vertices. So proton-proton interaction. So this is only one crossing of the LHC, one event, but it contains four interactions. And we will have to identify which one the beam is coming from. So this is something which is quite complicated in the analysis. So just to tell you how the LHC is working. So in red, the first line is the design, are the design parameters. So the LHC was designed to work at 7 TeV proton against 7 TeV proton, so 14 TeV in the center of mass, with a bunch spacing of 25 nanoseconds. So this is the 40 megahertz I was talking before. And at LHCb, an average number of collision per voltage crossing of 0.4, which gives a luminosity of 210 to the 32. But since its start, the LHC has been running at lower energy. It's 3.5 GeV against 3.5 GeV. So 7 TeV in the center of mass, and with a larger bunch spacing, but an average number of visible interactions in order to have a higher luminosity, so to have more events. And an 8 TeV in 2012. So the conditions are much complicated, are more difficult than anticipated for LHCb, but still it's working. So what to remember is that we have about 20 megahertz of bunch crossing, which leaves visible track, and in an event, which can contain several interactions, there is about 30 particles produced per interaction. 1/200 event contains a big quark, or a millibar pair, and we are looking for very rare branching ratio, about 10 to the minus 8. That's why we need this large number of events. And later on, I will explain you why we are looking at those rare events. It's not just because we want to suffer or whatever, but this is where the physics is interesting, and that's something we want to learn. So the one last very important point for LHCb is, as I told you, the trigger, which allows us to change from 40 megahertz of bunch crossing to go to a disk. We are writing on the disk at about 4 kilohertz of event. So we have to reduce from 40 megahertz to 4 kilohertz. So 10 to the 4 reduction. So how we do that? We do that in 2 steps. The first one is in the electronics. So we have some dedicated electronic circuits which are able to select energetic tracks or energetic photons. And because we know that these energetic photons or tracks are coming from B decays, this is a reasonably efficient way to select B decays. And this gives you gives an output of 1 megahertz. Okay? And then at 1 megahertz, we read the full detector. So here it's only in the subdetector level, some computation. And if it says, yes, it sounds like a B event, then we read out all the whole detector at 1 megahertz. And everything is written on a huge CPU farm of about 2,000 computers, which reconstruct the whole event and try to select useful decay, and then write to disk. on the event we want to see. When there are muons in our events, we are quite efficient. It's about 70 to 90% efficient. But when there is no muon, only hadrons, kaons, and pions, then the efficiency is lower, about 20 to 50%. And this is some kind of limitation right now. But still, we still have many events, but this is really already a limitation. Okay, so data taking. So this is the amount of data we've recorded. So LHC has started, in fact, in 2010. We recorded a very small fraction of data with which we already did some physics analysis, cross-section measurements. But then LHC was really on full speed starting from 2011, where we recorded about 1 femtobarn of data and then 2 in 2012. Now, since the end of 2012, the LHC has stopped for all experiments. It's going under repair in order to be able to run at 14 TeV when it will start again in 2015. This is maybe if you've studied accelerator physics, or you know when you're doing an accelerator and doing collisions, with time the luminosity decreases because because of the number of particles in the bunches is decreasing because of many effects. Beam-beam interaction, loss of particles, and so on and so forth. So when you collide two beams, with time, it decreases like that. And this is what LHCb and no, not at all. Atlas and CMS are measuring. GPD means general purpose detector, which means Atlas and CMS. But if you monitor the luminosity of LHCb, it's the red curve. So first, you see that it's lower. And it's lower because we want it lower. I told you that we need to identify which primary vertex the B is coming from because we need to measure its decay length, to measure its decay time. If we have a lot of primary vertex, if we have 2, 3, we can still work. But if we have 20, we cannot know which one it's coming from. So that's why we want a reduced luminosity. Here we would have 20 or even 30 primary vertices in the event. We don't want that, so we want to have a lower luminosity. And in order to have a lower luminosity, what the LHC is doing for LHCb is instead of defocusing the beam, so blowing up the beam, if we people first were thinking they would defocus the beam as in optics, blowing it up and then collide. It would give you a lower luminosity. But this luminosity would also decay with time because then you will have less particles. What we are doing is we are keeping the same focused beam, but instead of colliding them head-on like that, we are just slightly so you have to think that the beams are like motion, let's say. And instead of colliding them head-on, we're colliding them on the tail at the beginning. When there's a lot of particles in the beams, we're just colliding like that. And then, dynamically, when the number of particles is decreasing, we put them more and more head-on. So it means this way, we keep a luminosity which is flat. So it means that for a given run duration, 9 hours, let's say, which is a typical run duration at LHC, we proportionally have more luminosity than with the standard scheme. So this is the first trick LHCb has found to have as many events as we can in a clean environment, so not too many primary vertices. The other trick is what we call deferred trigger. The idea is that the LHC doesn't work point, so after, let's say, 10 hours or, I don't know, 8 hours, then the Atlas and CMS says, we don't have enough luminosity. Dump the beam and fill again the machine. Okay? But to fill the machine, there is some time, 1 hour, 2 hours, because it's complicated to fill the LHC. You start from a bottle of hydrogen, and then you have to put it in several accelerator complex to bunch them, and so on and so forth. So when it's about 2 hours. But during that time, the CPU farm I was talking about, the one with the 2000 computer, doesn't do anything. It doesn't have to trigger on events because it doesn't have events. So what we are doing is that we are using this time between the field to process more events. So here, we are taking apart 20% of the events, and we are putting them on this without looking at them, just like that. And then, in between, when we have nothing to do, we are looking at them and selecting whether they are interesting or not. So it's a way to have 20% more data. You can see it here. This is a measurement of the output rate, and this is an LHC field. So where we have beam, and here we have no beam, but this is what the computer farm is doing. So okay, it's working, it's working. But after there is no beam, it still works for some time, because it's processing, it's recuperated back this event. Okay, so this is the time scale. So in 2010, we have some very few events, and we measure some JPSI production cross-section. And then we go on from 7 and 8 viral with about 3 inverse femtobar. At that time, we have some measurements which are already more precise than the previous experiments, which were the B factories running at the Epsilon 4S at SLAC in Stanford and Bell in Japan. Then we are now, you see, we are here, which is LS1, long shutdown 1. So the LHC has stopped. It's going under significant checking to be able to start again at 13 or 14 TV there. Then we will take more data. And we will stop again so that we have a major upgrade of LHCb, and I will talk about it later on in this week, to have much, much more integrated luminosity. Okay, so that was all on the detector. Now we're going to physics. And I'm quite that's perfect.
And perhaps возможно, мы здесь перерывы сделаем.
No, no break. Haha. Forever. No break at all. So, CP violation. So you know everything about CP violation because of Sergei's lecture. And because, of course, of the other lecture you have had for some of you who have followed particle physics. I just want to repeat things in a more practical way, maybe. So, even those who have not done particle physics may have done optics and physics. And you've heard about interferences and the double slit experiment. So, the idea is that when you have two paths to reach the same point on the screen, you have interferences. In a way, for CP violation, this is the same. CP violation is interference. So, violation, you need to have two paths to reach the same final state. Okay? So as you need to have two, you need to have two amplitudes to reach the same final state. And then we find a way to perform twice the same experiment, one starting from a B, and one starting from a B bar, so an untied B, and we see if we observe the same result. So as Sergei said, there are three types of CP violation. So CP is, I have an amplitude A, which brings me from the meson B to the final step F. And if I apply CP, I have an amplitude A bar, which brings me from B bar to F bar. If there is CP violation, then the modulus of A squared is going to be different on the modulus of A bar squared. And there are three ways to obtain that. There is CP violation in the decay, where it's really in the decay that something happened, and this is the only one which can exist for the charge B. And we are going to see an example of that just after. Then, instead of doing it in the decay, you can have it in the mixing. So Sergei told you because of there is BB bar oscillation, so this is what we call mixing, which go from a B0 to a B0 bar or B0 bar to a B0 through box diagram. And you can have also CP violation there, and then you would observe CP violation. And then you can have a mixture of the two, which is CP violation, the interference between mixing and decay, like that. So each time I have, okay, let's stop there. First, let's discuss about the first one, which is direct CP, which is the easiest one to think about, at least to my test. So you've seen what is the CKM matrix. It's the 3x3 matrix, which encodes, in fact, in a way, the couplings of the W with the quarks, right? So here, for example, if I have a W plus which coupled to a U and a D bar, I have the VUD matrix element, which is this one. Then Sergei told you that this matrix is unitary. If it's unitary, it means I use this matrix times the U DAG1 is the unitary matrix, and you can write all the relation in a graphical way, which is this unitary triangle, which has sides and angles as any other triangle. And the gamma angle is the angle we are going to measure through this direct CP. It's the angle here, which is the phase, in fact, of VUB, because this is real, so this is the phase of this. So we want to measure the phase of the VUB matrix element. So I said I want to measure the phase of the VUB matrix element. So VUB matrix element means I should have a B and a U. Okay? So let's try to think what I can have as a diagram to reach to measure this angle. So the final step I'm trying to find decays of a B to U. Okay? So let's see. I can have this B to U, and it's the argument of VUB over VC. So this is a decay with B to C, okay, with VCB. And here it's B to U, so VUB, okay? So I'm on the good path. I will be able to measure the phase between these two decays. Okay, so let's try to write later on my Feynman graph. So I have a B quark here, a C here. Here I have a U bar. So here I have a D0, and then I emit a W, which can give me, for example, K minus. Okay? But here, what do I have? I have a C and a U bar, and here I have a C bar and a U. So this is not the same final state. I told you that I need two path to reach the same final state in order to be able to measure CP violation. So I nearly have the same final state, but not. So what can I do? I need to find decays of the G where I cannot distinguish if it is a D0 or a D0 bar. So for example, K plus K minus, pi plus pi minus. Okay? So if I choose well my D final state, I have the same final state which I can reach through this path or through this path. So I have everything at hand to be able to measure CP violation. Is everybody lost or not? You're not asking questions, so I'm going to ask you questions.
Could you repeat the question, please?
Huh?
Could you repeat the question?
Are you lost?
What?
Are you lost?
Me personally, not really.
Okay, I'm at least. Okay. Good. So, I have two paths to reach the same final state. Okay? So let's write the amplitude. So this one for D minus, this is I call AC because it goes to a C1. Okay? Then if I look at the other decay, I have an amplitude which is shifted by gamma because I have here a VCB and here a VUB. So the amplitude, it's the amplitude multiplied by the weak phase, gamma, so the phase between the VCB matrix element, and then I have delta B, which is a strong phase because I can have also strong interaction, strong effects in the diagram. Then I can apply CP. Okay. What happens if I apply CP? For the weak angle gamma, it changes side under CP, while for the strong angle, it does not, so it stays with the plus. These are amplitudes. So in order to observe something, it's an amplitude modulus square, okay, which I can compute, and I obtain that. Then, when you measure CP violation, you look at the different rates and you build the asymmetry. So the asymmetry is just that you count how many B minus you have, you compare to the number of B plus. Okay? And so it's the difference divided by the sum. And from the previous formula, you can prove yourself that it has this shape quite easily. You have three parameters here. You have gamma, right? The one you're interested in, the one which is linked to CP violation in the standard model. You have the strong phase, delta B. You don't care about it, but in fact, you need to measure it if you want to be able to know what is gamma. And then you have RD, which is the ratio of the VUB to VCB amplitude in size. Okay, then I see it's not very important for what we want to say. So that's the physics you are interested in. Now, let's imagine I'm reading a paper. I should have written the reference. I can give it to you later on. But now there is an LHCb paper on that, and I'm going to explain what's in it. Okay. So the first thing I told you, you need to select the event. And you want to know how your event was selected by your detector in order to handle the efficiency, the systematic uncertainty. So you say, okay, since I'm looking for into K plus K minus or pi plus pi minus. So I need to have some information from the rich detector in order to identify, to say I have kaons. You see here I can have even up to 3 kaons. I'm also using a control, so these are really rare events. This is of the order of, the branching ratio is of the order of 10 to the minus 3. I want also to use this mode where it's not really directly useful for CP violation, but it's 10 times larger. More than 10 times larger, so it's going to be a control mode. So in order to check that I'm understanding what I'm doing. Okay, so I want to, so two charge tracks, but I want to know either kaon or pion because I need to recognize this from that, And I told you that this one is 10 or 30 times larger than this one. So I need to be able to find which is which. Okay, so this is my P0, and then I will have a track for this bachelor kaon. And here again is another problem because instead of having the W which gives a K minus with a VUS here. You can have a W which gives a U, a pi minus here. And this has a branching fraction much larger by a factor of 20. Okay. And so then you tell me, why don't you use that one? Okay. I don't use that one because of the following. Because if I would use that one here with a pion, I need to have a pion here. Okay? And to have a pion here, this has to be a D quark. Okay? And this is very rare because it's a CD. It's a CD matrix element. So I would have something which is very unbalanced between the two amplitudes. And if it is very unbalanced, the balancing between the two amplitudes is RB. Okay? It's the ratio RB. So if it's very unbalanced, it will mean that RB is going to be very, very small. But if it is very small, I will not measure this. Because this is going to be close to 0. And I will never see sine gamma. So I need to have RB as large as possible. So that's why I'm using the K minus, the D0 K minus final state and not the D0 pi. But, unfortunately, there is this mode, which is a pollution, which is much larger. And this, I need to be able to distinguish a pion from a kaon in order to kill. So I will separate my two samples into two parts. One where this track is more kaon-like and one where it's more pion-like. Okay. We're going slowly through the analysis. Okay, so we are happy, we have a D0K, but in fact, what do we really have? We have two tracks, okay, and a kaon. But we can have other modes which gives two tracks and a kaon. We can have what we call charmless decay, so decay without D0. And these are a branching ratio. If I put all the branching ratio, which is about 2 orders of magnitude larger. Again, so this is 2 orders of magnitude larger. So this is potentially very dangerous problem. So how do I recognize? it has to be compatible with the D0 mass. Here I have all the events, all the invariant masses. It has no particular value. So first it will remove the significant part of that. But still it's not enough, because some will be by chance near the D mass. So then there is a lifetime, yes. It's the lifetime of the D. Because what we want to select from a topological point of view, so this is my primary vertex, proton-proton collision. The B flies, it decays into a kaon, the bachelor one, and a D0. And the D0 has a small lifetime, not as large as the B, but still significant. It flies and decays to pi plus pi minus. The background, what we want to reject, primary vertex, B events, and then the three tracks are attached to the B vertex. I told you that we have the velo detector, which is so nice to measure the impact parameters and things like that, and we use that. In fact, we compute the vertex of the two pions, and we look how far away it is from the vertex of the B, which we know from the kaons. And so the flight distance between the B vertex and the D vertex, okay? And this is to show you, so this is Monte Carlo, and this is the significance of this vertex. So the vertex divided by the error. The distance, divided by the error. And you see in red, this is the signal. It's a log plot. So this is the signal. And in black, this is the charmless background. And you see that it is cutting above the blue line is very powerful to reject a lot of this background. So experimentally, this is what we are doing. Oh, and then, okay, so this is what Monte Carlo tells you, but you never trust Monte Carlo. If you're an experimentalist, this is something you have to keep in mind. Be careful with Monte Carlo. You have to cross-check it on data, always. So what you do, you look at your D sideband. What is the D sideband? I'm computing the pi plus pi minus invariant mass, and I'm doing the plot. We look like that. So this is the D0 mass. And then you have candidates everywhere, and the D sidebands are here, okay? So I'm looking at the D sidebands, and I'm plotting for the events there, what is the B mass, okay? Look at the dot of the line, and this is what I see. I see a distribution with a large peak at the B mass. And this is the charmless background. It's not a D, so this one, it's not a D, so it can be there, but if I have a K, it should be a B. So this is exactly what I see here. I see a nice B. Now, I apply that blue cut, which I found on Monte Carlo, and I check what I have. I have this one, the pink thing, and you see that I've killed my peak. So the cut is doing what the Monte Carlo tells me. It's really killing this background. And at the end, I can look at my result. I've done the whole analysis. Now let's look at the result. First, I will look at the control. You never look directly at your result. First, you look at some control sample which you understand what is in, and you see if indeed what you measure is what you expect to see. So this is this control sample. So D0 to K minus 5 plus. So these are really LHCb plot. I've copied them from an article. So what do you see? So there are 4 plots. So here it's B minus, here it's B plus, okay? So if I go from here to here, this is CP violation. around, which is about 20 times larger. This is the D0 pad, and you see you have a very nice peak here. When you select the bachelor track to be pion-like. If you select the bachelor track to be pion-like, you have a very nice peak too, but still a little bit of pollution due to this. Okay? It's shifted because you're assuming it has the Keon mass, so it gets shifted a little bit. So it helps you to recognize it. But still, you have a very nice B minus peak here, and a very nice B plus peak here. They are very clean signals. You may still find that there is background, but compared to previous experiments, it's much, much more cleaner. Okay, so this is it. Do you think I see CP violation here? No, I heard no. No, I don't. I don't expect to see some. So it's reassuring that I don't see some. So now, let's take a D mode, which is K minus, K plus, K minus. For example, it's similar for pi plus, pi minus. So K plus, K minus. Here I expect to see CP violation, yes? Because it's the same final state I can reach. And here you see that from here to here, I don't have the same number of events. Okay? This is CP violation. Here, I see the same. I don't see CP violation. I have the same number of events. Okay? They are compatible, the two. Because I told you that I need to have a balance, two paths which are of the same size roughly. And here they are very different for the D-pad, so I see a very tiny effect of CP violation that you don't see that high. But here, you have a significant CP violation effect you can even see that high. Okay? So at that point, you stop and you say, good, I've seen CP violation. You compute the asymmetry. No, no, no. Not at all. Because you can have asymmetries which are not at all CP violation, and you have to check. You can have many other causes to for CP violation. The first one, yes?
Can you give some examples of other causes of asymmetry besides CP violation?
Yes.
Oh, sorry.
Yes. So, first, you have slightly different numbers. You can have some slightly different numbers of B plus and B minus produced. And if I start from two different sample in size of B plus and B minus, even if I don't have CP violation, I will not have the same number. Okay, everybody agrees with that? How can I have, so this is called the hadronization asymmetry. So production of B plus and B minus slightly different. So why is it so? It's a little bit complicated, but so we have two protons in the final state, okay? So in fact, because it's two protons and not a proton and an antiproton, you have a slightly higher probability to pick up a D quark than an anti-D quark. So this because we have proton and not antiproton. And in fact, we measure, it's predicted by the Monte Carlo, and we measure it. Here we measure the ratio of lambda bar over lambda. Lambda is the barrier, okay, the strange barrier. And this is 1. And you see that we are not measuring, this is the black points, at all 1. We do not agree with the Monte Carlo, but we are not measuring it either. The Monte Carlo says there is a difference, but we're measuring something else. Anyway, it's different. Data tells you it's different. So if we have more diquark than anti-diquark, it means we have more baryon than anti-baryon. Okay? And if we have and you can write it on a paper on your own, and you see it's not complicated, but just seeing it like that. So at the end, it tells me that I have a little bit difference than a little bit less B minus than B plus. It's very small what I measure on data, but still I have to correct for that. Okay, so this was the first way to have asymmetries which are not CP1. It's tiny, but still you have to take it into account. The other one is more experimental, and it's linked to the fact that the K plus and K minus interacts differently in your detector. If you look, for example, at the PDG, the measured cross-section of a K minus on proton is of the order of 22 millibar for a given energy. I think it's 10 GeV here. And for K plus on proton, it's 17 millibar. Okay? So it means that your K minus will interact more in your detector. So what's the consequence? So now, this is LHCb. So this is the Velo detector. There is a tracking. There is a magnet, some other tracking. The one reach. In fact, there is another reach. If a track interacts in the detector, it means that, for example, the K minus starts there, and then it interacts and starts to create nuclear fragments or things like that. So it will not be seen as a real track in your detector. Okay? So it will be only some hits there, but you will not see it, you will not measure it as a track. Or it can interact with a calorimeter and it will not give a good trigger, for example, because it has interacted in the calorimeter, in the electromagnetic calorimeter, and it hasn't reached the hadronic calorimeter. So you will not see it really in your detector. So it means that this is it will be lost. So it means that you will lose more often the K minus than the K plus. And this is very bad, because imagine that you have a number of, imagine you have no CP violation. I have the same number of D0 K minus and the same number of D0 K plus, and I lose some of them experimentally, then I will claim my CCP violation, but this is not true. Okay, so this is the interaction, but it can also happen that your detector is not working well. So the bending, we are seeing here in the bending plane, it means that when the polarity is up, let's say in the magnet, all the plus particles are bent this way and the minus this way. Okay? Now imagine that you have some dysfunctioning or less well functioning part in your detector. Okay? So this, if it is in the up part, I will lose more often the minus particle. And again, it will give me an asymmetry in the towards the plus particle. I will see more plus particle than minus particle. So this is an asymmetry, an observed asymmetry, which has nothing to do with CP violation, which is a detector dysfunctioning. So what we are doing there is we are changing the polarity of the magnet. Every week, roughly, we are changing the polarity of the magnet. So it means that instead of having that, I have that. So if this part is badly functioning, it will kill as many plus than minus tracks. Okay? Very good. But at the end of the day, you can build as complicated thing as you want. You need to test it on your data. And this is, we are testing it using this B to D0K and D05 with the D0 between K minus 5 plus, where we know we can't have CP violation, but all the other asymmetry will be present. So we are measuring them from here. the CP asymmetry. We know there is no CP asymmetry in this. And then we have the production asymmetry, the kern detector asymmetry, and then we can extract them directly from data. So then, from this plot, the correction I just described, we are able to measure this asymmetry for the pi-pi mode and the k-k mode. And you see that we have a significant asymmetry, which is of the order of 15% with an error, especially in that case, which tells you that for sure there is CP violation. This is less significant because the branching ratio is much smaller. And you see here the yields from the peak, so these are the two peaks I've shown you, where we saw by high the asymmetry, remember? Okay, so I've described you the simplest way to measure CP asymmetry in a decay final state. In fact, people are very imaginative. They find many other ways, they build many other ways. At the end, it's always to be able to reach the same final state. Because if there is nothing else you remember from CP violation, there is only just that. You need to have two different paths to reach the same final state. So people are just finding modes to reach the same final state with not too unbalanced path so that you measure CP violation. Okay, so I'm not going to describe all that. But if you put together all the asymmetry together, then you're able to extract gamma, which we are interested in, and RB. You remember? These RB here. Yes? We need to have RB, we need to have delta, B, and we need to have gamma. We want to have gamma. So, gamma versus RB, gamma versus delta B. Delta B, we are not that interested, but we need to have it. We need to extract it anyway. So, this show you. Okay, so in brown, this is the result of what the analysis I've described in details. In blue, this is another analysis. And if both are combined, gamma is measured to be about 67 degrees, plus or minus 12. And this is extremely precise. This is the most precise measurement of gamma today. Well, it's not extremely precise, but this is the most precise. We want to measure. We will see, no, we will not see, but I will tell you about the upgrade of LHCb, and the goal is to reach 1 degree. So factor 10 degrees. Okay, but it's still a long way to go. So this is a plot similar to the one Sergei has shown you. And you see the angle gamma, and the angle gamma is not precise yet with this 12 degrees. So if you want to really see if all the measurements agree, you need to have each of them very precisely. And gamma is very special. Gamma from these decays is very special because it has the diagram I've drawn here. There are these three diagrams. It means that there is no loop diagram, no box diagram, so in principle, we do not expect physics beyond the standard model in those diagrams. So it's a kind of reference point where we think we have no physics, no new physics, no physics beyond the standard model, and we will compare with other measurements where maybe new particles can play a role, and maybe they will not give the same gamma measurement, as Sergei explained for sin to beta and sin to beta effective. violation, which is a CP violation in the mixing. I just wanted to, so I'm not going to describe the physics a lot because Sergei has described it, but I wanted to say a word about it because it was something which was 2 years ago, everybody was talking about that because people were hoping that they were seeing new physics. So physics beyond the standard model. The physics that we were all looking for. So CP violation in the mixing is strongly related to the mixing phenomenon, which relates the mass eigen state and the flavor eigen state. And if you, since they are not the same, when the bee propagates, you have through space and time, you have some passing between the two states. I'm not going at all to repeat all that. This is what Sergei said. What you have to keep in mind is that solving the Schrödinger equation, doing some math, which are lengthy but not very complicated. At the end of the day, you can write the time evolution of a B0. So if you produce a B0 at time t equals 0, then you can see its time evolution and compute it at time t. Same for a B0 bar. Here the bar should be on the B, not on the 0. So I can compute them like that. Okay? So these are not very nice. You can see there are some hyperbolic sine, cosine. You have the lifetime difference between the two mass eigenstates, the mass difference between the two mass eigenstates. And from that, you can compute the probabilities. Okay? And in fact, the probabilities of the B0 to decay as a B0 bar, so to have mixed, is this formula. The probability for a B0 bar produced at time t equals 0 to decay as a B0, so to have mixed, is this one. They are the same except that. So if Q over P, the modulus of Q over P is different from 1, it means you have CP violation. And this is what people are looking for. And experimentally, it's always the same trick that we build an asymmetry. So we look at how many B0 bar produced at time t equals 0 decays as B0, comparing how many B0 produced at time t equals 0 decays as a B0 bar. So the difference divided by the sum. And from the previous formula, you see that it takes this shape, which, nicely enough, doesn't depend on the time anymore. You don't need to measure the decay time. You just need to count. Okay? And this can be done for DT and BS. In the standard model, this is expected to be extremely small. It's not very visible, but it's predicted to be of the order of 10 to the minus 4, 10 to the minus 5 even for the BS. So this is it's not because it's predicted to be small that it's not interesting to look for it. If the standard model predicts you it's 0, then if you measure something, it means you found physics beyond the standard model. So this is usually what experimentalists are doing. They select modes which are clean experimentally and where you do not expect to see any effect. And if you see some effect, we found something. So the idea is that you have two types of ideas. One where you just identify your B through its minotonic decay. So let's say you have the B and the gamma, and then so it's a W minus, and then it's a L minus. So here you have a U minus. If you have a U plus, it's B bar. So you're counting how many times you have mu plus, because if you have two mu plus, it means since you're producing a B0 and a B0 bar, it means that you have two B0 bar. If if you have nu minus, you have two B zero. So you have mixing, and you see the difference between the two. It doesn't tell you if it is BS or BD, so you have both. You can also reconstruct DS, so just to identify whether it's BD or BS. So this was a big thing that excited people for several years even. So this was an analysis from B0, where they measure 0.8%, and you see it's significant. When you have 0.8%, you have nothing. If it's 0.8 plus or minus 12, but it's 0.8 plus or minus 0.2. So it's significant, okay? It's significantly different from 10 to the minus 5, which was predicted by the standard model. So people were very excited, theorists were very excited, and they're saying, oh, come on, this is new physics, and so on and so forth. It's a very delicate analysis. You have the same problem as always in CP violation of this asymmetry due to the detector. So they were doing magnet polarity, they were doing several things. It's proton anti-proton as a tevatron, so you get rid of one asymmetry, but still it's complicated. And at the end of the day, they were able to say the CP violation for the BD and the CP violation for the BS, and it was different from the standard model. You see, this is the standard model, this is the BD, this is the BS, this is the standard model prediction, which is tiny and precise, and this is what they measure. So people wanted, so when you are like that, you need another experiment to tell you. And I'm not going to describe the other experiment. This is a measurement of LHCb. It's always the same. You have to cross-check what you're doing. You have to measure it on data as much as possible. I leave it in the slide. And at the end, this is the result. So this is the CP violation in the mixing for the BD. This is CP violation in the mixing for the BS. So this is the standard model. So here it's another measurement from D0. This is the dimuon from D0 I described. Then the B factory has done some measurement. This is here. They are on top of the standard model. And this is LHCb, which is also on top of the standard model. So unfortunately, it seemed that this effect was either an experimental uncertainty which was not properly taken into account, or also a statistical fluctuation, because you always have to keep in mind when you're doing an experiment that statistics can be surprising and you can have a statistical fluctuation. So it seems that we have not observed physics beyond standard model in CP violation in the mixing, as we hoped for some time ago. So I think I'm going to stop there.
Thank you. Question, please.
So, in the case of the evaluation, you say that you have 50% of CP evaluation, yes? It's considering asymmetry of the not CP evaluation. Asymmetries in the asymmetries in the of different processes, not CP evaluation.
It is CP violation.
It's only
because this is really the correction from the detector is very small.
Can you please show slide 34?
34?
And you have also developed some reasons which can cause this difference in the first place. Yeah? And why such difference
I've discussed, it's very small, okay? So 1% maybe. So let's forget about it for what I want to say. So I'm counting the number of events, okay? So the number of V plus minus the number of V minus divided by n plus n V minus, okay? This is what I'm doing experimentally. And then I'm saying, I'm sorry, I'm going to write here. So I'm saying that it is RD, so I'm very bad with formula, so I need to, okay, I'm not going to write it, it's here. This is that, okay? So what is what? So the most important thing here is RD, and RD is the ratio of this B to U transition to B to C. In case RD for a B to decay is of the order of 0.1. RD for a B to decay is less than 0.01. So an order of magnitude smaller. So this is why, even if it is the same gamma, the effect I'm going to measure is tiny. Okay? So if I would have an extremely huge sample of events, I will also see CP violation in the other. But it will be so small that now I cannot see it significantly.
Is it a good idea to study P bar collisions in order to have the same probabilities of creating quarks and antiquarks?
Yes, yes. That was the good thing at Tevatron, because we have P and P bar. So theoretically, yes, you would love to have P and P bar. But practically, it's building an anti-proton beam is much more difficult than a proton beam. So it's more complicated to have enough, the large number of proton per bunch you want, or anti-proton per bunch you want to have very good luminosity. That's why people stopped doing PP bar collision and they went to PP collision. But theoretically, yes, if there would be no practical details in the accelerator, yes, of course. Yeah.
And I have some questions. First of all, I want to return to the first part of your lecture and to ask what is the general structure of muon system in more detail. Like RPCs.
Yes, RPC.
On the RPC, no rich chambers, no controlled strip chambers.
Is more experimentally. It's a small. Yeah, and it's a small part.
Okay, and another question is why CMS detector can be used for LHCb experiment?
For CP violation measurement, for example.
No, what specific structure, like adjustments in LHCb experiment allows it to be like more adapted for this measurement?
Okay, so first the fact that we measure very, very well the vertex position. It's even slightly more precise than in CMS, but not tremendously more precise. The second point is that we are able to recognize pion from cairn, which they cannot do, basically. And this is a huge. You see the decay versus dpi. The question you were asking, why don't I see it in dpi? If I would not be able to recognize dpi from decay, I would be swamped by this background and I will not see simplification. So kpi identification, and the last one is trigger. Because they want to do X physics, so they need to trigger on a muon of the order of 20 GVPT, for example. Okay? We want to do D physics, we want to trigger off muon of less than 1 GVPT. And having a data acquisition which is able to go from there to there, it's not
you said that before colliding the beams face to face, or instead of colliding them face to face, firstly you have them on some impact parameter,
Yeah.
and then you decrease this
Yeah.
impact parameter. Could you please tell by which technique this impact parameter is controlled? How is it measured?
So,
If it is
so the
measured.
position of the beam, basically.
Yes,
Well, the position. So
relative position.
the technique by itself. I don't think.
Just to measure multiplicity, and you have to adjust multiplicity. So multiplicity is proportional to the number of interactions.
So you just adjust the beams and you see how much there are collisions, yes?
Yeah. In special runs.
So it is not.
Oh, okay. Yeah. The controlling.
But what you need is to adjust luminosity to this state, and you don't need to measure it at first. Other possibility would be defocusing techniques.
But this is not good because we are losing luminosity. You flat there.
Yeah, but this is.
That's what I explained. It was not good. I think the focusing is not good. But and then I think they have also a beam position monitor that just to check all over the ring that it's where the beams are and so on and so forth. And then they have done some calculation before, but it's an ad hoc measurement of the overall luminosity and the monitor.
Okay. Could you show us slide number 49? I just wanted to see the slide.
You wanted to see it? Okay.
Okay. Is there so much more question? Okay, thank you very much. Если хочешь какие-то вопросы, отдельные задать, пожалуйста, подходите к лекторам. Полная свобода действий. Tomorrow, 9 o'clock.